Ladies and gentlemen, boys and girls, welcome back to another lesson of transparent physics. In this episode, we are going to be continuing our series on energy, work, and power. And specifically today, we're going to be teasing out an issue that comes along with gravitational potential energy, specifically issues concerning height. All right, let's see. By the end of this episode, you should be able to calculate gravitational potential energy, although that was introduced in a previous episode. You're going to be able to use the concept of reference height, but there are some challenges associated with reference height, so we're going to talk about two ways to avoid running into potential pitfalls. And as a quick aside, if you find that the video was helpful in helping you understand this topic better, please consider liking the video when the episode is done. If you have any questions about what I talk about or comments about how I did it, please leave it in the field below. And to learn more about what's coming next from Transparent Physics and to help this channel grow, please consider clicking the subscribe button. All right, then back to the physics, gravitational potential energy. So if you want to store energy in a gravitational field, it can be done. You just take an object, you lift it up, and bada boom, bada bing, you've stored energy. The amount of energy that you store depends on the weight of the object, which is m times g, and the height of the object, represented by h. You smash all those together into one equation. You have PE equals mgh. We have the little g there as a subscript. I probably won't use that very much more often throughout this series, just because gravitational potential energy is really going to be the only potential energy we're going to be talking about, at least right now. Again, the units work out to be joules. We talked about how the SI units combine together to give us a J for energy. And as far as the calculation goes there, m times g times h, m's not going to be an issue at all. G, watch out for, just make sure you don't make g negative. It's just going to be the magnitude, probably going to be 9.8 meters per second squared. But again, this physics applies anywhere in the universe, so you can switch it around if you're on vacation. And h may not at first glimpse seem to be the problem child here, but h really is the point of difficulty moving forward and will be the focus for the rest of this episode. Okay, so at first blush, it might seem kind of weird that height would be an issue that we're going to stumble over, but let's talk about that in the context of a construction site. You can see we have 3 workers, 1 worker in the basement, 1 worker on the ground floor, and it says a 3rd worker is up on the roof. I don't know, looks a little more like the attic the way I sketched it, but either way is fine by me. And the issue here is that when they're in the building at different heights, they each look at measuring height in a different way. They're not all going to measure the same height of the same object because they are standing at different points in the building. What I mean by that is, let's say there's a worker, the red worker on the ground floor is gonna hang some sort of fixture. He'll probably measure the height where he needs to drill from the ground. He's not going to measure it from the basement. He'll measure it from the floor where he's standing on. The worker who's up in the attic, when she measures something, even though she understands what the ground floor is, she's not going to probably use the ground floor as a reference height. She's probably going to use the beams that she's walking on as the reference height for whatever she's measuring. And the person in the basement, obviously it would make sense to him to be like, well, when I'm measuring, I'm going to measure from the height of where I am. So the 3 individuals all are measuring 0 meters from their own individual sort of frame of reference. None of them are wrong. They're all just looking at it from their own perspective. So the workers are doing their job, and then one of them says, "Hey guys, where'd we leave those blueprints?" And there's a roll of blueprints that someone left on the 2nd floor of the building. We'll just assume for the record that each floor is, say, 5 meters in height, and we'll assume that the blueprints have a weight of 10 newtons. So when the workers are they're all looking at the exact same tube, but because they're sort of using their own frame of reference to look at it with, we see that when we calculate gravitational potential energy, each worker is going to see the tube as having a different gravitational potential energy. Think of it in terms of like how much energy it would have if it rolled off and fell down like on their foot or something like that. So the red worker has the blueprints 5 meters above them. So if the tube was to roll off and fall, it would start with a potential energy of 50 joules, 10 newtons times 5 meters with respect to the red worker. The blue worker sees the exact same tube, but to the blue worker, it is much higher up with respect to their starting point. So if that tube was to potentially fall down to their height all the way into the basement, it would be starting then effectively at a height twice as high, so the potential energy would be twice as much. And it gets a little weird when we look at the worker who's in the attic. She looks at the tube, and actually she wouldn't be concerned at all with that tube rolling down and hitting her in the foot, because it couldn't. It's at a height lower than her. So with respect to her, the height is actually negative 5 meters. It's 5 meters below her. So the potential energy is negative 50 joules, which seems a little bit weird maybe to talk about it as a negative value. But think of it this way. It sort of says, hey, if you want to raise that tube up to her height, you would need to add 50 joules just to get it up to her height. That's basically what the negative potential energy means there. So what we see is that all three workers look at the exact same tube, and they see the tube has different gravitational potential energies. And again, every one of them, it makes sense for what they're looking at it, but I think you'd agree with me, this is not a way to move forward with, to have everybody getting different answers just depending on where they're standing in the building. That could lead to a lot of confusion. Whew. All right, I think you'd agree with me, we're in a bit of a pickle right now. Obviously, you'd agree with me that we can't get three different measurements for the exact same scenario just based on where somebody's standing. That would seem to lead to all sort of chaos and calamity, but don't worry, just take a long sip of tea. And it's all going to work out. So to deal with the problem associated with different people seeing different potential energies based on their height, we have two solutions we can employ in introductory physics. The first solution is what I call the executive decision. If we've got a problem where everyone is seeing different potential energies because they all have different reference heights, then don't allow people to have different reference heights. Decide a single reference height that is going to be the one height to rule them all, and just force everyone to measure from there. So let's say in this instance you've got the three workers. Again, they're all seeing the blueprints as having different potential energies, but let's say that red is the shift supervisor, and he says, hey, measure the blueprints with respect to my height, people. So when he does that, then blue measures with respect to red, green measures with respect to red, and everybody agrees that the potential energy is the same. Yeah, maybe it's not the most elegant solution, but textbooks will often use this approach when they're asking you to solve for the gravitational potential energy of an object. They might say something like, hey, measure this with respect to the ground, because technically there's lots of different ways that you can measure it, and your teacher doesn't want to see like 37 different creative approaches to what initial height you should use to measure from. So the textbooks will just say measure from this point, and that way everybody gets the same answer every time. All right, so that's scenario A. Hey, there's nothing wrong with an executive decision. It's a great choice for introductory physics students. I, however, kind of prefer this next approach when dealing with this scenario, because it actually recognizes the idea that potential energy itself isn't really that important just alone. We want to look at it in the context of the larger problem. I can look at any object sitting on any shelf and I can tell you its gravitational potential energy, but the world's not really a better place for that. But what we can do is not so much focus on what the potential energy is, but look at it if there's a change in potential energy. Now, change is represented by the delta symbol, so change in potential energy. It's the same equation, we just throw some deltas in there. In this case, we're going to assume the mass is the same. We're going to assume the gravitational acceleration is the same, but it's the height that's changing. When you calculate change in height, change in anything is always final minus initial. Watch out especially for negative signs. That's an excellent place to trip up when you're doing these calculations to start off with. So looking at it in the context of this problem, let's imagine that the blueprints actually drop from the second floor and they roll down to the first floor through a gap in the rafters or something. And now we have a situation where the potential energy of the blueprints has changed. From the perspective of the shift supervisor red, the object started at a height of 5 meters. It ends at a height of 0 meters. So its change in height is negative 5 meters. It's 5 meters below where it started. Interestingly enough, if you're the blue worker in the basement, again, it starts at 10 meters and it ends at 5 meters. So it's 5 meters minus 10 meters. Again, you get a change in height, which is negative 5 meters. And you can probably predict what's going to happen, but let's take a look up at the green worker. She's looking at the blueprint. It drops. Again, here's where the negative signs can get a little confusing. It is final minus initial. So the initial height is negative 5. The final height is negative 10. So it's negative 10 minus a negative 5. And that also still, believe it or not, does work out to be negative 5 meters. So every worker can keep their own reference frame. They can all measure the heights any way they want to, but the fact of the matter is those blueprints have dropped 5 meters. And changing your reference point is not going to change the fact that the blueprint has dropped 5 meters. And I think that's a really elegant way to deal with this particular scenario. Because the same change in height for the same object always gives the same change in potential energy, regardless of what height you're looking at to start. One or two points worth repeating as we wrap up this lesson on gravitational potential energy. First and foremost, you can absolutely have a negative gravitational potential energy. If the object is located below where you consider to be 0 meters, it's got a negative height and a negative gravitational potential energy. That's not an issue at all. Totally acceptable. Also, you can have two people look at the same object and disagree about its gravitational potential energy. Depending on where they see their reference heights, they could both do the calculation exactly correctly and end up with different values. And again, we're not super comfortable with that in physics, so we need to sort of iron that problem out. And there are two approaches to deal with it. Again, we can make that executive decision where we simply say everyone has to measure from a certain height. But remember, we can sidestep the issue entirely if we are looking at scenarios where the potential energy changes. Then everybody can have their own individual reference heights, but the change in potential energy is going to be the same for everyone. And again, personally, that's my favorite way to look at it, but you can make your own choice. As always, thanks for watching. I hope I've made the issue of choosing quote-unquote the right height a little clearer for you on this episode of Transparent Physics.